Adam Shelley is going to be introducing our speakers. So I will let him go ahead and introduce our first speaker.
Hi, everyone. So our first speaker is Jennifer Shackelford, and she will be talking today. Her talk is virtual field trips to your park, an inexpensive way to reach the masses. Jennifer is the educational specialist at Mammoth Cave National Park. After teaching for 9 years in the public school system, Jennifer began working at Mammoth Cave and sharing her love of the environment with students from across the nation. Thank you. I'm going to hand it over to Jennifer and let her speak.
Thank you. Good morning, everyone. It's nice to be here, and I'm pretty excited to talk with you all about this because no matter where you are, you can do this so inexpensively. And Mammoth Cave, a few years ago, we didn't have any type of virtual programming. And when I was first hired for the position, that's one of the things they wanted to begin. And I was really scared at first because it was so new to me. I'd never used Zoom or anything like that 4 or 5 years ago. So I'm going to share my PowerPoint right now and just kind of let you all learn about what we do here and how we started doing that. So can I get a thumbs up if you can see this virtual field trip PowerPoint? Thank you, Marissa. All right, so it all began about 3.5 years ago when I first got hired and I got to go to the Grand Canyon for a 2-week training called Fundamentals. It's a Park Service thing. And while I was there, I went to the studio for the Grand Canyon's Environmental Education Department. And it was fancy. They had all kinds of fancy stuff, and I was very intimidated. I talked with the education specialist there to find out how much it cost, and it was thousands. I think it was like $30,000 or $40,000 that they had put into this system. And I knew that my budget for environmental education supplies at Mammoth Cave was $2,500 a year. So I wasn't going to be able to quickly implement something like the Grand Canyon had. So what I did is I talked with our IT people, and for about $20, we bought this little camera that you see in this picture, and it's what I'm using right now to talk to you all as well. I've had it for about 3 years, and it's just up on top of my monitor. It's a very inexpensive webcam, and you put that up, and that's really all you need. You need some good internet, which is something we don't always have at our parks. So I sometimes work from home because I have better internet at home. So I am at work today hoping that the internet stays happy so I get to keep talking with you all. But that's it. You just need a computer, some internet access, a little inexpensive camera. And if you can spend a little bit of money, and it doesn't have to be expensive, later on I'll show you what's behind me. It cost $1 at a local store. It's just a plastic tablecloth for $1, and I have it taped up behind my desk. So right now at home today, I have rangers that are working with students from all over. They're doing virtual classrooms today from their houses, and they have plastic tablecloths hung up on their walls. We like to use Zoom. We sometimes use Microsoft Teams because that's the type of email we have here at the park. Google Hangouts is also pretty simple to use. So any of those platforms, they are free, especially if you use the shorter version. So Zoom, if you're not going to be on for more than 45 minutes, it doesn't cost anything. So most of our programs are definitely less than 45 minutes because we, are not paying for any of these things. We're just using them through those platforms for free. Now, you might be asking, how do we work with thousands of students every year? The way we do it is we have kind of an in with the teachers. And this is something that I suggest for any of your parks. This morning, when I was listening and you all were talking about science-based things, I got so excited because I was hoping whoever was watching right now would think, man, this is something we could implement at our place right now. So we work with a local university, and every semester, any teacher or actually a student who is getting ready to become a teacher in the elementary education department at Western Kentucky University, they come here to Mammoth Cave. Dr. Janine Huss, who I think might be on here today, is amazing, and Mammoth Cave has worked with Janine for years and worked with Western for years, as was talked about earlier, I think, in some of the sessions. So these student teachers, before they go out into their elementary schools, they come here for the day, and we do all kinds of curriculum-based programming with them. You can see here we're in Great Onyx Cave, and this is a young lady who's teaching now, and she has a magnifying glass and she's checking out the gypsum up above her. In the bottom picture, they're doing an activity from Project Wet, which is one of the project curriculums that some of you all may have heard of. Project Wet, Project Wild, there's all different kinds of really great curriculums, but it's about the water cycle. So of course, anything we do here at Mammoth Cave, it has to be connected, you know, to the park, to our mission. And so we're teaching these student teachers how they can go into their classroom and teach the students about the water cycle and about Karst and Mammoth Cave. And because we have about 50 student teachers, excuse me, every semester that come to Mammoth Cave, they then immediately, a few months later, go out, and most of them hopefully find a school to work at and have a classroom. So that's one reason we're able to do a lot of these programs, is because we see these teachers right before they graduate. So we're fresh in their mind and they're interested in booking programs. Another way that they can find us is just on the internet. They can get online and go onto our website and click on distance learning, and it sends me an email and we can book programs that way. I don't know if you guys read hashtags, but I'm being sort of trying to be silly here. A few years ago, or actually, yeah, December 7th of 2018, I don't have Twitter or anything like that, but I have a sister that does. And she sent me this cracking up and was like, "You really need bangs, Jennifer." So this is another way that we have teachers contact us. This is a teacher that's from out of state, and he put this on the internet, and then other people saw it, and then they contacted and said, "Oh, we saw you on the internet. We would love to do a Google Hangout with you." So once you get out on social media, it's really easy for people to find out about you and contact you. So this was South Dakota, actually, a school in South Dakota. And we don't have any kind of fancy reservation system for this, because I have to look in my calendar and see when we have openings. So they simply either make a phone call or they send an email. And once they send that email, I send out what's called a confirmation form. And this is another reason I think we have a lot of buy-in from teachers. We're not just on the computer talking to the kiddos about just whatever. We are specifically talking with those students about one of these subjects that deals with Mammoth Cave. So we can talk with them about fossils, geology, water cycle, weathering and erosion, Kentucky history, that's also part of Mammoth Cave, point, non-point source pollution. So any of these topics you see on the screen, we will come up with an individualized program for that classroom. And as someone who had a classroom for 9 years, as Adam said earlier, in the public school system, there were some visitors I loved to have them come into my classroom because it really went along with the content, with the curriculum I was teaching. And then there were other days when they left and I thought, oh, you know, in my head, that was 45 minutes that I probably should have been teaching, because it was a bit of a waste of time. I would never, of course, say that to their face. But we try to make sure any topic, any activity that we do with these students on the computer, that it is going to be worthwhile. So we send out this list and then they complete a form like this. So for example, we will be working with a local school, Austin Tracy Elementary, virtually here in a few weeks. We'll pop on the computer at 9:15, just like I did today with you all, and we will have a classroom of 21 students from Mr. Davis's class. Then later on that afternoon, we'll work with Miss Hensley's class. And I'm not sure how well you all can see this, but he wants us to develop a model using an example to describe ways the geosphere, biosphere, hydrosphere, and atmosphere interact. So what we are going to be doing on that day with those students is we're doing an activity about the carbon. It's a carbon cycle activity. So we have lots of different activities that we have developed over the years in the environmental education department. And that's one that sort of goes along with that science standard. And I'm not sure how many of you all are familiar, but what this is the next generation science standards is what he's used down here and put into the paperwork. And those are national standards that we have here. So, of course, here's one of my favorite places in the cave. Just wanted to share this. So we have over 52,000 acres above ground, so we can talk with the students about that, you know, below ground, and then of course above as well. One way that we get a lot of funding here at Mammoth Cave in the environmental education department is we write grants, and that grant funding helps with things like procuring new laptops so we can work with these students and things like that. So this is a form that we send out to all of the teachers afterwards. It's just a how did we do form. At the top, it has a little bit of information asking if they came to Mammoth Cave during one of those student teaching workshops. And so this is just so we have some really great stats for grants. We can say, you know, of the 400 teachers we worked with last year, 32% came to Mammoth Cave during their block education class. So once again, if you are able to work with a local university, I would suggest that you come up with some kind of form like this to help you get those statistics. Also, we like to know how they found out about us. How comfortable are they teaching environmental education? Because we can do a professional development with their school if they're not comfortable teaching those topics. And then on the back, it just has an area where they talk about what they liked, what they would have preferred we do, something like that. So how do we define success? Whenever I have new rangers that start working here, they always want to know, well, how do I know if I'm doing okay? I just want to know that those students are enjoying themselves. And if they are having fun, then they're learning as well. So we try to make these programs interactive. Unlike today, I'm sorry, we would stop a lot during our actual virtual programming with the classrooms and let the kids ask questions. And also we make the activities where they are somewhat interactive. And that is all I have for you guys. So I'm going to stop sharing. And I think our time is about up in a few minutes. Hope you all enjoyed and learned a little bit about how perhaps you could do something like this at your place of work.
Great, awesome. Thank you so much, Jennifer. That was really great. I did not get any questions from anyone. So if someone has a question right now, you can, I think you can either ask to unmute yourself or send me a message right now and I can unmute you.
How did the teacher in South Dakota find you?
That teacher actually found us on the web, like on the Mammoth Cave website.
So I'm from South Dakota, so I just wondered what the school was.
Yes, I often get emails. There's a link on the website and people will click on that link and then it comes to me and they'll say, hey, just saw this. I'd love to do a program.
We do have a question from Chris Groves, I believe. I'm going to unmute him really quick and he can ask his question.
Yeah.
Chris, you should be unmuted.
Yeah, thanks, Jennifer. I guess the question I have is that you had a long list of topics, insects, geology, and how do you develop those units in the first place? I guess, you know, you develop a bank of them, but what are the sources of information used to create them in the first place?
A lot of the activities are from those different project curriculums like Project Wild, Project Wet, Project Underground, Project Learning Tree. Some of them are things that we found over the years, like on the internet. Some of them I brought, you know, a few when I came from teaching, kind of tweaked them, and different rangers who have worked here over the years have done that as well. Sometimes we just sort of make them up. We needed a geography lesson a few years ago. We kept having teachers want topo map stuff. And we had a really hard time coming up with something that would be easy to take into a classroom, and then go to the next classroom, after 30 minutes. We can't take big giant stuff because we are moving from room to room when we are in those schools. So we came up with what we call the Topo Map Cowbell game. It's one of our favorite games. And all you need is a cowbell and a few topo maps. You split the kids into groups and you just ask questions. So we lay the Mammoth Cave topo maps out in front of them. And we can also do that virtually now by showing them a Mammoth Cave topo map. And you just ask a question like, if you're at the Sloan's Crossing Pond trailhead and you go cross country east, which trail will you end up at, or something like that. And then they run up and ring the cowbell, or virtually they can see who types in the answer the fastest and stuff. So lots of different ways that we found them. But if you are ever around, come to the Earth House and we can show you. We have a building that has probably over 200 activities. They're all in tubs, alphabetized, and they have lesson plans with them.
Awesome. Thank you so much, Jennifer. There's a bunch more people who actually want to ask you questions. They're all in the chat. I believe you can see them because I think most of them were responded to everyone. But we do need to keep on time here. So I think James is going to introduce our next speaker. I believe I'm going to be playing her presentation. Yes, Val, for you. If you're, I think you're muted here.
Yes. So
there you go.
The next speaker is Val Hildreth-Werker, and her presentation is Cave Conservation and Restoration Workshops Around the Globe. I do not have a bio for her, but if she's around, we can let her.
Val, are you're there?
Hi there. Yes, can you hear me? I'm unmuted. Okay, yep. Are we there? You see us? Okay.
Yeah. Did you want me to play the presentation for you?
Oh, I think that's a good idea because our internet here, I can tell that everybody in our tiny town of 70 people is getting online, and it makes the video come through really well.
All right, so I'm going to share my screen, and Val has pre-recorded her presentation. We'll listen to it, and she is happy to take questions at the end.
And we have a little intro to Geomorphological, my husband and me, within the presentation, so we'll go with that. I also do have it up and ready to go if we need to go to plan B.
All righty. Well, all right. Let me know. There are some noises in the hallway. I apologize.
Thank you for joining us online for the UNESCO Karst 2020 conference.
Can everybody hear the sound? Yes. I can't see any of you. So if somebody can hear the sound, yes?
Sustainable current best practices in cave conservation and restoration with this introduction to our international workshops. The first principle for everything about caving should be primum non nocere. First, do no harm. By way of introduction, here we are. My husband, Geomorphological, and me, Val Hildreth-Werker. For over 20 years, we've served the National Speleological Society in the U.S. as Conservation Division Chiefs. This is our big book of cave conservation and management, published by the NSS with support from the National Cave and Karst Research Institute. The volume offers 600 pages with 46 peer-reviewed contributors who collaborated with us in defining current best practices. The book describes sustainable, state-of-the-art, science-based theory, strategy, and a lot of nose-to-the-flowstone practical techniques. Cave conservation is always an evolving process. We encourage finding new minimum impact solutions informed by science, technology, and field experience. While working on the book, Jim and I began to coordinate collaborative workshops. We've conducted seminars, workshops, and training events for various federal, state, and municipal agencies, universities and institutions, conferences and events, corporate sponsors, show caves, private landowners, conservancies and nature preserves, as well as UNESCO World Heritage Sites. We work in close collaboration with an individual or a small team who know the cave venue. Our collaborators coordinate the logistics, speak the language, understand the workshop participants, and work closely with us in planning and presenting the workshops. It is an honor and pleasure to partner with these fine cavers from around the globe and with all of you as partners in international cave conservation. As examples, we'll use detail from 3 very different workshop events. With our partners from Brazil, left to right, Vitor Moura, Luciana Alt, Augusto Auler, Geomorphological, and me. We prepared and conducted a 7-day international training course using 2 show caves in the Brazilian state of Minas Gerais. The workshop was held in Gruta Macané and Gruta Redemato and was sponsored by the Instituto de Karst, Brazil's Karst Institute, and Anglo-American Mining Company. Through an intense application process, 30 participants were hand-selected for this first training course from among federal, state, and private environmental protection professionals, mining company officials, biologists, geologists, and archaeologists from academic, federal, and private venues, plus environmental lawyers, show cave managers, interpretive guides, and cavers. Each day we had 2 to 4 hours of classroom theory and activity. For some, this was their very first look at a cave map. Every day we spent many hours in cave with small teams identifying issues, making decisions, assessing impacts, and getting in there with hands-on success in addressing a variety of nose-to-the-flowstone applications with the accompanying frustrations and the rewards that come from long hours of mitigating human impacts and giving back to a cave. Teams adapted their plans and techniques as they encountered unexpected situations while performing the tasks. 7 days provided plenty of time for trying out a variety of real-time restoration and management methods, and gave us great one-on-one time for questions and interaction, group discussion, thinking through challenges, considering options, exploring sustainable solutions, impact mapping to identify issues and plan strategies for restoration, organizing team presentations. We even found time for sorting show cave rubbish that blossomed into a spontaneous art statement in the parking lot. With brick and rubble removed from the cave, this team made a structural statement representing the Macané cave entrance. Lado lixo, Portuguese for trash can, a contemporary art photo message to the public. Another conservation partner, Ferdinando Di Donna from Italy, invited us to do a workshop to augment technical skills for the Puliamo il Buio, or Clean the Dark campaign. He coordinated with the Italian Speleological Society to bring our workshop to the Nuoro region of Sardinia for an international rendezvous of 1,500 cavers. During our workshop spanning 2 days, 20 participants explored cave conservation and restoration through classroom theory, team interaction, and in-cave projects. We were in a wild, undeveloped cave for hands-on practice during this workshop, and to protect the cultural and historical significance, small teams first assessed and documented the markings, carefully tested techniques, and photographed processes as they monitored their progress in removing contemporary graffiti. This team came up with a clever idea. Use 2 cell phones to quickly capture and document before and after photographs in one image. Teams tested various tools, vigilant to employ a really light touch, made a few typical here's an overzealous faux pas, and discovered solutions. You can pixelate and blend away the scar using natural materials from the cave. Participants began to do some speleothem repair with training in the proper use of more archival museum-grade epoxies. Apply the special cave-safe epoxy only in the middle of the break. Stay away from the edges to avoid epoxy squeeze-out along the break joint. In the workshops, we learn a lot from each other, we accomplish a lot, and take a lot of new information forward to the next cave project. Our partners from the classical karst in Slovenia are Rosana Cerkvenik from Skosians Caves Park, a UNESCO World Heritage Site, and Micha Prilovsek from the Karst Research Institute of Slovenia. Together, they organized the logistics for our workshop, which was held during the International Conference on Sustainable Management of Show Caves at Skosiansky Yama. They arranged for national TV coverage of the full in-cave workshop, with participants initiating projects in flowstone cleanup using only brushes, sponges, water, and clean exam gloves, photo documenting progress and techniques, mitigating footprints. If the impact results from anthropogenic activities, then fix it or clean it up. However, if the impact is from natural occurrences, like the drip marks at the top of the image, then we usually leave it be. Footsteps can be camouflaged by retexturing to blend the imprint, because visible footprints will invite others to follow, and the imprints will increase. Participants removed old piles of spent carbide. We demonstrated an introduction to speleothem repair. And in the classroom, we explored other speleothem repair techniques and the necessary archival products and materials. In-cave removal of clearly contemporary graffiti, working in teams to test the techniques and achieve tangible results, inventory assessment of anthropogenic impacts, photo document and monitor work in progress, and plan future ongoing restoration events. Typically, our objectives are to train in conservation standards and techniques with didactic theory and practical application, and to initiate and motivate the continuation of cave conservation projects after the workshop. Our workshops help advance cave conservation practices that protect natural and cultural heritage. Sometimes people ask, can you really restore a cave? Yes, cave environments can be restored. We can't take a passage back to a completely pristine state, but we can restore it to a former condition. We can help promote a return to ecological balance. Here's an example. Human activity can introduce harmful things into cave habitats, like industrial particulates, lint, residue. Over time, the anthropogenic impact builds up and changes the native cave ecosystem, but it can also be cleaned up, and the spelean habitat can be restored to a former condition. Here's how we found this cave entrance. Yes, graffiti can be cleaned up, but only after careful inventory and assessment for cultural and historic markings. Contemporary graffiti is laboriously removed and the cave is restored to a more natural state. A cave pool before we cleaned it, with silt left behind by careless footsteps tromping through the clean aquatic habitat, and after delicate restoration to a more pristine state. Here's how we found this broken stalagmite. Formations can be repaired to stand and or hang strong again where they originally grew. In this final section, we'll introduce a few of the minimum impact guidelines from our workshops. A PDF with bullet points for generic minimum impact caving is available with this presentation. Each spelean environment is unique. Workshop participants have developed protocols for specific caves and protocols for specific disciplines in speleology. Always look before touching and think, what will I damage? Is this a necessary hold? Learn to use minimum impact caving techniques. Dirty gloves leave imprints on handholds and cave walls. Instead, use the cleaner back of your glove. Sometimes all we need is a knuckle or a fingertip for balance. And after restoration, use a clean exam glove and touch only a small spot. To protect pristine areas in caves, use clean powder-free vinyl gloves and then move gently and efficiently through the special area. Catch your crumbs and carry everything out of the cave. There's no need to introduce more organic carbons into often low nutrient cave environments. minimum impact caving, reduce the need for cave restoration, protect the caves and the resources they harbor. We thank you for joining us, and we welcome your questions and discussion. So please feel free to contact us with ideas, comments, questions, workshop concepts. Jim Worker at caves.org and Val Hildreth-Werker at caves.org.
All right, great. Thanks, Val. So if anybody has any questions, I haven't been able to check the chat here since I was screen sharing. Let's see. If anyone has any questions, feel free to message me so I can unmute you real quick, or just send me a message with your question. My light's turning off. 1 second.
So one question, Val, in case you can't see it, and Marissa had stepped away, is, are there any suggestions that you have for caves that get repeated graffiti?
Suggestions for caves that get, oh, good, there we are. I was trying to share my screen with you, but I don't know. Anyway, you managed to do that, thank you. Okay, caves with repeated graffiti. Yeah, sometimes they're called party caves or sacrificial caves. We don't agree with that. We like the idea of going in and using those caves as community projects for outreach, because yes, caves can be cleaned up, and in the process, community members as well as policymakers and those in the cave and karst community, cavers, speleologists, it's a great place for everyone to come together and do cave cleanup projects, in the process learning a whole lot about cave and karst systems and the importance of the natural and cultural heritage. Also, by then going forward and including some kind of kiosk, some kind of messaging, we've seen this work so that we have a cave near Albuquerque that's open to the public with thousands of people visiting every month, literally thousands. Stairway going up to this cave that is a historic archaeological dig happened in this cave. We did find evidence of prehistoric markings on the cave. We also found historic markings associated with that Hibbins dig site. And in doing a massive cave cleanup by bringing in a specialist in rock art restoration, we got a lot of media attention, and now there's monitoring with several trail groups, cave groups, and we've had to clean off very little new graffiti. So the idea is change the culture of the people going in and making the graffiti, give them ownership, and they will help spread the word and help stop the graffiti.
Great, thanks, Val. There are a couple other questions for you in the chat if you want to answer those, but we got to keep things moving along here. So Adam, if you'd like to introduce our next speaker.
Yeah, so our next speaker is Kathleen Webb, and she'll be presenting the 2020 Mammoth Cave Natural Resource Condition Assessment. And Kathleen Webb is the Associate Dean for Research and Professor of Chemistry of the Ogden College of Science and Engineering at WKU, and the Director of the WKU Applied Research and Technology Program, which is 8 shared core facility labs. Thank you.
Okay, share screen. Okay, so the 2020 Mammoth Cave National Park National Resource Condition Assessment is actually a report that probably took about 5 years to actually complete from start to finish, and that's actually a little bit longer than how many of these National Resource Condition Assessment reports take, but we also have what we consider one of the more complicated park reports to do. Chris Gross, Autumn Singer, Leanne Bledsoe, Rick Toomey, Bobby Carlson, and Katie Algio are all co-authors on this, and I have to say I consider that all of my co-authors had a greater impact on this report than I did. So bearing that in mind, I will proceed. Okay. Okay, so Mammoth Cave National Park was established in 1941. This park, we've heard lots about it today, and I really can't begin to tell you how important this park is to this region. I will say, one of the reasons I moved to Western Kentucky University from my prior institution was because of Mammoth Cave National Park and the opportunity to have it as a convenient field site. Okay, the National Resource Condition Assessment Program of the National Park Service establishes a framework to evaluate the condition, the natural resource condition of a park. It actually is best to think of it as a snapshot. So this is the condition of the park now. And the concept here is to use credible science to report on conditions and trends and to identify critical data gaps and threats. So what we are trying to do is inform the National Park Service, other stakeholders, the general public, what the condition is now, what are potential threats, what are critical data gaps, where should resources be put. The National Park Service, of course, has to be very strategic about its resources. And so knowing what the short-term condition is and a very thorough analysis and framework that has been established for the park allows consistent planning to take place in the future. So these condition assessments really are meant to last and to serve as a foundation for decades in the park. So the framework really starts with scoping meetings. So we had many meetings with staff from Mammoth Cave National Park and the Cumberland Piedmont Inventory and Monitoring Network, and multiple meetings discussing what was important, because there are a lot of data that is available, a lot of files, a lot of people's personal interest. So clearly we could not, and no NRCA reports on everything. What you do is you establish framework that's mutually agreed upon by all of the stakeholders for what is appropriate baseline conditions and natural resources. So we, after tough discussions, established 13 natural resources to inform our framework. And the framework is has three basic categories: the physical landscape. So of the physical landscape part of the framework, we established 4 resources: surface air, cave air, geology and soils, and hydrology and water resources. In the biological realm, we established 6 natural resources to report on: bats, birds, herps, native communities, surface aquatic communities, and cave communities. And finally, after much thorough discussion, the human influence. So we focused on fire management, night skies, and human impacts. So the approach for the NRCA is very prescribed. So the National Park Service wants a framework category established. For instance, in the framework category landscapes, you have a series of resources. So under the series of resources, we have surface air. There might be a number of indicators for the surface air, but our primary indicator would be air quality. And the measures that we finally established or agreed upon to indicate the air quality were visibility, particulates, ozone levels, NOx, and mercury. And so the measures were what each individual measure was then investigated and an indicator of air quality established, and that was used to evaluate the entire resource of surface air. So indicators have 3 parameters that have to be established. The condition status, that is it stable? Is it improving? Is it decreasing? That's the trend. The condition status warrants significant concern, warrants moderate concern, or is in good condition. And then finally, the confidence in your assessment. And the important reason that we have to establish confidence in assessment is because of the types of information that we use for each of the individual measures. For the air quality measurements at Mammoth Cave National Park, all of these parameters have high confidence in assessment. That is, the measurable experimental approaches needed to determine visibility is well established, is measured routinely, has good quality and good quality assurance and control on every one of these parameters. But that is not always true. Even though it's might be an important indicator, your confidence in the assessment might depend on reports that were written 10 years ago or 15 years ago. And the methods that people use might not have been thoroughly explained. So the concept of an indicator and the confidence in it actually depends a lot on the source. And so one of the reasons why an NRCA takes so long is that the people who agreed to do the NRC, they don't actually collect the data. So we didn't actually collect a single bit of data for this report. What we did is data mine. So we did private interviews, we collected resources, we did literature reviews, we did what I would call gray literature. That is, we went into files that weren't at Mammoth Cave National Park that weren't necessarily published. We used personal resources, we used photographs, we used whatever we needed to use to gain a sense of the status and trend for the indicator symbol. And then we also use that to try to establish a good reference condition, so that we could have a consistent measure whether it is improving. Now, reference conditions for the parameters that I have, the measures that I've indicated for air quality, surface air quality, are very good. But again, the reference conditions may be relative, or it may be the best possible information. So you establish your reference condition to your best possible ability. So let's take a look at the data for Mammoth Cave National Park. And so the air quality station at Mammoth Cave National Park is in Houchins Meadow, and that's actually just right on the edge of the park. And the data that we've chosen here is annual haziest and clearest days from 1992 through 2017. And so this is daily views. And so if you see, the haziest days in red are actually trending down. And the clearest days in blue are also trending down. We have a natural condition assessment for haziest days and a natural condition for clearest days. And the clearest days are going down in terms of overall numbers, and the haziest days are going down. So that's a little inconsistent. And you would say, okay, air quality in terms of haziness is improving, but in terms of clearest days, it's not improving. And so what we would say for our indicator is visibility. The measure was a haze index, and the status is that although there is some significant improving trends in both best and worst haze conditions, conditions remain in the area of significant concern because we are far from the natural condition for clearest days. And this is just one measure for one resource for one indicator. So another parameter that we looked at was sulfur deposition. So sulfur deposition can be wet sulfate, dry sulfate, and dry sulfur dioxide. And if you see, the wet sulfate contribution is decreasing. The dry sulfate deposition is decreasing, and the dry sulfur dioxide deposition is increasing or decreasing. So all of these measures are decreasing, and so sulfur is the indicator. The measure we actually used was wet deposition, and wet sulfur deposition warrants moderate concern because it's still pretty substantial. Based on the estimated wet sulfur deposition of 3 kilograms per hectares per year, the trend in total wet sulfur concentrations in rain and snow at MACA, Mammoth Cave National Park, actually did improve. And so this is our indicator status and trend symbol. And so this is very interesting. There are actually 3 parameters here. The arrow indicates that the measure is improving. The arrow goes up, or the arrow goes down, or the arrow is even indicating stable. So that is one way of looking at the trend. The dark black lines surrounding the yellow circle indicates we have high confidence in the data. We had moderate confidence in the data, this would be a thinner black line. And if we had low confidence in the quality of the data, excuse me, I need to go back. So this would actually be a dashed line. And the color indicates the status. So yellow indicates that it warrants moderate concern. Green says that it would be in good condition, and red would consider that it would be a significant concern. So these little symbols are actually pretty, what I would call compact information. Challenges.
Kate, I just want to let you know you got about 1.5 minutes left.
Well, then I'm going to go through this. I'm almost done. The white nose syndrome. This was a significant impactor on our bat populations in the last couple of years. Native plant communities, we have a lot of non-native plants and there are issues. The emerald ash borers are threatening the park's ash trees. We have potential threat to our hemlocks. And of significant concern is agriculture and other land use contamination draining into the Karst aquifer system. Interrelationships, I will skip over this, but to indicate that this NRCA report actually concluded that the Mammoth Cave National Park is well understood, well cared for, and carefully protected, and that many of the resources are in good condition or even improving. Acknowledgements, there are so many people I need to acknowledge. I'm going to just go right through it. This report was one of the most complicated technical reports I have ever been involved with. And it was impossible without the great support of Mammoth Cave National Park and Cumberland Piedmont and all of the staff and scientists involved.
Great. Thank you so much, Kate. All right, we're gonna keep on moving here. Adam, would you like to introduce our next speaker? I'm going to be playing their PowerPoint from
absolutely. So our next speaker is Cory Holliday, and the presentation is forest management considerations and best management practices on karst landscapes, a lesson in the evidence-based management guidelines. Cory Holliday is the Cave and Karst program manager for the Tennessee chapter of the Nature Conservancy. For over 15 years, Cory's work has focused on protecting karst resources and advancing research critical to cave and karst conservation.
Awesome. And I believe Cory is here. He may have some time to take questions at the end of his presentation, but I am going to be sharing that with you all right now. Okay.
Hello. This is Cory Holliday. I'm a Cave and Karst Program Director for the Nature Conservancy. And today I just want to talk a little bit about forest management on karst and exploring developing evidence-based best management practices for forestry on karst. So this all came about for me through the Nature Conservancy's Working Woodlands program. This is a program that was initiated through our Pennsylvania chapter to improve sustainable forests and conservation forestry on private lands in North America. So each Working Woodlands project has to be at least 2,000 acres in size. They all receive FSC certification, and we enable and empower private landowners to participate in the private carbon market and sell carbon sales through analysis and marketing of carbon resources that is done through the Nature Conservancy. So the first Working Woodlands project to come to the Tennessee chapter is in a really highly developed karst area, and it's indicated by the star on this map. And then the color shading on this map is indicating cave density in Tennessee. And Tennessee really does have a lot of caves. We've got nearly 11,000 known identified caves in the state now, representing about 20% or a little over 20% of caves in the United States. And the property in question, it has been an income producing property for a family since the 1960s. And they're conservation minded, but primarily have held this property as an investment and to produce income for their family. In this map, you can see the parcels, just kind of the general shaded area, a little over 3,000 acres. The red and green dots are known cave entrances. The white dots are the low points of identified sinkholes. The pink sort of shaded areas with darker pink outlines, those are delineating the sinkhole watershed. So each one of those is identifying, delineating a closed depression with a closed watershed. And then the gradiated sort of pink to red color scale is just indicating the depth of individual sinkholes. So you can see, especially the western half of the property does have a lot of karst development, including this one, really big sinkhole here in the western and southwestern portion of the property that's, it's over 150 acres in size and 120 feet in depth. So when our forest management director, our forest director, Trish Johnson, came to me with this project, she kind of said they had forest management plan they needed to write, and there were some karst features out there. Would I mind taking a look at it? And at first, I was really amazed at how much karst development there was, but I knew that there had been a decent amount of work put into developing forest management on karst, and I just figured I'd pull some information from some of those and make an easy day of it. But when I reviewed the plans I could find and ones I was familiar with, I was a little taken aback. They were very well written, very thoughtful, and really good plans. The only real problem was that there was not a lot of consistency between plans, sometimes even within single agencies in the same geography. But more than that was just a general absence of rationale and references for the guidance being prescribed. And the Nature Conservancy, we're a science-based conservation organization, and we try really hard to build measures into the work we do, and really be able to answer the why questions when developing any of our plans. So we dug a little deeper, looked at more international forest management plans on karst, and just did a generalized journal review, looking for anything that may be relevant to developing best management practices for forestry on karst, as well as supporting what we saw in the good plans that we did find. So I'll just run through some of the data we found that I thought was relevant to forest management BMPs. It's obvious, I'm sure, to everyone here, but worth noting in a forest management plan that karst landscapes are vulnerable and are more so compared to non-karst landscapes. We found a decent amount of data relevant to karst features and their ability to support sort of forest resiliency in the face of climate change, and to serve as sort of buffers and islands for remnant species. Not a good amount of information specific to sediment loss and sedimentation in response to forest management. Specific to sediment loss and karst features, we couldn't find a whole lot. I found one paper that actually was measuring sediment loss and sediment flow from erosion in sinkholes. It was in a military installation, and it was a good paper. The really good take-home from that I thought was really relevant was that vegetative buffers didn't seem to work in the presence of concentrated flows. So just something to be aware of when developing BMPs and forest management plans. We wanted to try and get to the root of some of the cave ecological drivers of caves and karst systems. And crickets seemed to be something that there was a decent amount of information around. And they are also just kind of a ubiquitous allochthonous energy input for karst features in caves. They're coming out at night, foraging around cave entrances, and then bringing that energy back into a cave or karst feature. And certainly practices and management around those cave entrances have the ability to impact those crickets and their ability to find food and bring it back into those caves and karst features. And it was one of the rare places we actually found good data and numbers and things, numbers to support best management practices and some of the guidance that we saw in other plans and that we were developing. And then just more generalized around karst feature ecology, we wanted to kind of understand the roles of dissolved organic carbon versus particulate organic carbon and the associated concentrated flow versus diffuse flow. And we found a little bit of information around those where healthy, deeper soils do have an ability to absorb water and release that slowly over time into karst features, sort of supporting life over this longer period and providing this diffuse input of dissolved organic carbon, whereas other systems may be more flashy, or you may have seasonality associated with concentrated flows and higher levels of particulate organic carbon, and those can be really important as well, and in supporting sort of seasonal breeding and things of that nature for some cave and karst endemic organisms. And it appeared in the research that there was a balance to be had between those two, and you really didn't want to monkey with it too much. And then regarding bats, you can go down a pretty big wormhole. We try to stay with research relevant to bats associated with karst features and forest management around karst features. We did find, a lot of evidence supporting the concept that bats in North America are relatively imperiled as a group. We found a good bit of information about bats breeding around caves and karst features in the fall in much of temperate North America, and using trees and forests in the vicinity of caves and karst features during that time. And it was even bats that don't hibernate in caves or aren't going to hibernate in that particular cave or karst feature. And then we found some additional gray literature specific to white nose syndrome and sort of supporting the idea of optimal habitat directly adjacent to known hibernacula, and how that may impact or improve bats' ability to survive in the face of white nose syndrome, sort of coming out of their hibernacula and having this really optimal habitat to roost and recover in for a period before they may migrate to their summer zones. So we tried to find sort of this right balance of supporting the best conservation and sustainable forests, while also recognizing individual landowners' needs to draw income and their desires to manage their own forest for profit. So ultimately, anything that we were really prescribing, we wanted to be able to answer why. And we fell a little bit short. We really couldn't find enough supporting evidence to support the practices that we thought were important for karst conservation around forest management, but we kind of did the best we could. And we also, where we couldn't find enough supporting evidence, we tried to pretty much copy the streamside management zones that are in existence for freshwater streams. And we felt like, some of the biggest management issues around forestry on karst are directly relating to sediment loss and erosion from water, moving across the surface and into the underground environment. And we felt like, at the very minimum, if we mimic streamside management zones, we should be covering our bases, or at least have rationale to do so. So we did develop some generalized karst landscape guidance. We created definitions of surface features of karst, things that would be easy for foresters to understand and identify in the field. And then we created these karst management zones that are very analogous to streamside management zones. We did feel a need to classify sinkholes a little bit separately. So class 1 sinkholes would be a more broad, shallow sinkhole. Class 2 would be a deeper, more steeply sloped sinkhole, maybe a little more vulnerable to erosion. And then class 3 is anything larger than 10 acres. Anything bigger, you try to buffer larger than that, and you're really taking a big chunk out of a landowner's potential profits. And ultimately, we just couldn't find justification in the literature to support buffering those at such a large scale. So these are the general KMZs, the buffers that we came up with. We, buffered caves at 200 feet, and sinkholes, sort of basic sinkhole at 25 feet. A class 2 sinkhole would have an inner and outer. And again, that inner and outer language is very analogous to existing streamside management zones that foresters are familiar with and deal with all the time, as are these slope-based buffers. We try to mimic in these class 2 sinkholes and the swallets what was already existing for those SMZs in forest management guidance. And then the class 3 sinkholes, we gave those a straight buffer of 300 feet, but that is from the low points in the sinkhole rather than from the rim. And these are, much better described in our management plans, as well as the publication that we put out subsequent to this work. And then swallets, we really wanted to kind of treat those as streams. The input points were buffering all the way around, but then upstream from that input point, we just wanted to buffer them as a stream. So next steps, we're working towards incorporating this guidance that we developed into existing BMPs, as well as the Forest Stewardship Council standards. We're working to develop some improved graphics. That was something that was really, really useful in some of the existing management plans that we found. And then more than anything else, just filling research gaps. There's a lot of work to be done to really help us move forward and increase adoption of improved forest management practices on forest. So these are some of the publications that I've referenced. Our publication is on top through the National Cave and Karst Management Symposium proceedings, and then these other 3 are just really good forest management guidance documents that I found. I'm happy to answer questions anytime. Feel free to reach out to me if you have specific questions or would like to talk about this further down the road. Thank you.
All righty. Thanks, Cory. We don't have time for questions right now because we really do got to keep things moving along. But if you do have any questions for Cory, feel free to message him in the chat or send it to everyone, and he can look out for those. All right. Would you, Adam, like to introduce our next speaker?
Yeah, so our next speaker is Justin Carlson, and he'll be presenting middle to late Holocene soil geomorphological history at Crumps Cave and Sink, potential implications for soil conservation in karst terrains today. Now, Justin is the project director with the Kentucky Archaeological Survey. He utilizes geoarchaeological methods to examine human environmental interactions and landscape responses through the Holocene. Justin, if you will.
All right.
Great. And Justin, I'm going to give you a timer at 8 minutes and 10 minutes. It probably sounds like a cell phone. I don't know if it came through last time, but I will give you that. So just so you know.
Okay. So I'll get going here. All right. So I'm an archaeologist, and a lot of the work that I do at archaeological sites actually centers around soils and what you can learn from soils in terms of climatic changes in the past, environmental events, and also how people impacted the environment in the past throughout the Holocene. So at archaeological sites in karst landscapes, you can actually learn quite a lot. And I'll talk about an example today, Crumps, Sink, and Cave. These types of karst features are catchment basins for sediments and soils, and they actually have some really interesting environmental information. And you can look at them over a long period of time. And because of this, you can see how a landform has experienced certain events over that time. And I think these kinds of studies could be useful for land management considerations. As Cory was talking about earlier, karst soils are susceptible to erosion. So let's talk a little bit more about it. So the region I'm talking about today is within the interior low plateaus, and you can see that little orange dot. That is the location of the study area. All right, so all this really began with my dissertation research. And I had a question, and it involved the Big Barrens grasslands that were in the sinkhole plain in the Pennyroyal Plateau of Kentucky. Some ecologists had argued that they had formed through anthropogenic practices such as burning. And the reason for this is because when early European settlers arrived in the region, they actually came across a prairie-like landscape. But over time, as they pushed native populations out, woodlands started growing again. So this is one of the pieces of evidence that was used for this. So the ecologists argued that Native Americans were probably managing this environment in this region. It's not quite clear when the Big Barrens first formed, although we have some evidence that I'll talk about. It's possible it was during the Middle Holocene in the hypsothermal or the thermal maximum. This was between 8,500 and 4,500 years ago. Warmer and drier conditions. There was a lot of erosion throughout the interior low plateaus at this time, potentially because vegetation structure was less. But when we look into the late Holocene period, 4,500 to 3,000 years ago, a time of wetter conditions, we actually see a story emerging suggesting that grasslands were expanding at this time. So Jackson Pond is not too far away from the study area. It's in the sinkhole plain or just on the edge of the Dripping Springs escarpment. And at this site, you can see grassland expansion in the pollen cores after 4,000 years ago. So this is during a time when you would not expect this expansion. So what is going on here? Well, between 8,000 and 3,000 years ago, we're starting to see some major shifts in how hunter-gatherers during the Archaic period are interacting with their environment. For example, they start creating these formal tool technologies towards woodland clearance. On the right, you can see some grooved axes, and on the left, you can see some pestles that would have been used to process nut mast. So there's potential of silviculture. Later on in this, between about after 5,000 years ago, you see the domestication of plants such as sunflower and chenopodium. And this is seen at Mammoth Cave through Patty Jo Watson's work originally at Mammoth Cave. At the same time, through the interior low plateaus, we have between 4,000 and 2,000 years ago, there is a major increase in charcoal in the pollen record, suggesting that something is happening to create perhaps anthropogenic environments. Okay, so that's what I wanted to look at. Okay, so this is our case study to see what happened in the past in this region. And I did this at Crumps Sink, and I wanted to see if I could see in the soils a record of these activities at a site that actually has archaeological material, using a soil geomorphological approach. So if we have events like the Middle Holocene and we have erosion throughout this region, you should be able to see that in sediment accumulation or landform instability. If we have periods such as soil development, such as forest expansion, you might see soil development indicating a more stable landscape. So Crumps ended up having a record that spans 7,000 years. And just to show you quick, here's the site location on a map. You can see it's in the sinkhole plain in St. Louis and St. Genevieve limestones. It's a hollow karst landscape. There's little to no surface drainage within the sinkhole plain. And so these sinkholes were actually good places for hunter-gatherers to access water. All right, so just a quick look at Crumps Sink. You can see the rim of the sinkhole. It's actually relatively flat. I won't talk about the cave today that's associated. I did some work in there the following year after this, but I won't be talking about that today. So in 2009, my dissertation advisor, George Crothers, cored in Crumps Sink to see if there were archaeological materials and what extent there were. And he found over 3 meters of deposit. And so he thought it was very promising. So in 2015, I went there to test some of these questions I've been talking with you about at the site. And I put a 1 by 2 meter unit. So right there is what you got. And this unit ended up going down 3.8 meters. We had to shore the walls with floor jacks, screw jacks, and George was really helpful with that. But let me show you the profile that we got from this. Okay, so we got 4 meters of deposits here. All right, one of the really cool things is we have a great artifact sequence from the middle to late Archaic periods. These two time periods, during the Archaic, they actually span the middle and late Holocene transition. But I won't talk too much about projectile points today. I'm here to talk about soils. So after excavating this unit, one of the cool things that popped up was these slightly darker layers. And you could kind of see them. Some are more faint than others, especially the lower ones. And I was curious, like, is this a cyclical thing? What is going on here? Are these buried soils? Are these times of potentially more stable conditions? And are the lighter layers in between, are these times of sediment accumulation that might indicate erosion around the landform? So I got 12 radiocarbon dates from nut charcoal. So this nut charcoal gets there because archaic groups are actually processing nut mast, and the charred remains are left behind. And it gave some really interesting information in terms of dates. So we have dates from 7,200 to about 2,900 years ago. So when it comes to the research question, I'm interested in the middle and late Holocene. We have captured that, and we've captured the transition between those two periods. Middle Archaic is when we're seeing that groundstone tool technology really starting to kick into gear. And by the late Archaic, we're starting to see activities such as silviculture and later on domestication of plants, which continues into the woodland period. So we have a really cool record here we can look at in relation to cultural events and environmental events. Okay, so I've got these soils here. Well, I think they are. I think they're stable surfaces for a specific period of time. How do I test this? So this is where I use some techniques, some lab work, and I did things like magnetic susceptibility, and which is basically trying to. I'll tell you a little more about it later. Loss on ignition analysis and soil micromorphology. So a suite of different techniques in addition to the archaeological record to understand what happened on this landform. Okay, so on the left of this slide, you can see some squares in the profile. I think I can actually point things out. There you go. There's a square. There's a square. Some are more rectangular. So these are actually soil micromorph samples I'll talk about a little later. But for our purposes right now, we also collected loose sediment samples every 5 centimeters, all the way up the profile. Okay. In addition to this 3.8 meters, I put an auger test down to 5.2 meters beyond the archaeological deposit. And here's what we got. So magnetic susceptibility. When you see spikes in magnetic susceptibility, this could be an indicator of soil formation. So for example, if you have all of these, you have water, you have bioturbation, animals moving through the soil, organic additions, you could have an increase in iron oxides. And so these should be present in soils, or they should become more clear. All right. Another potential addition, another potential thing that could increase magnetic susceptibility is camp activities, such as, or burning. So say Native American use of fire. So here's the first thing I just want you to look at. Okay, so we have a line here. And if we look below the line, you can see it kind of flat lines. There's not as much going on. But once you get into the archaeological deposits above that dashed line, you can see a lot more going on in terms of additions to the soils. And this has something to do with how archaic hunter-gatherers, through their camp activities, they are already creating signatures in these soils. And that's pretty fascinating. It shows that even small-scale activities can leave a lasting legacy in a soil. Okay, so let's look next at these buried soil horizons. So these dark layers. So you got our dark layers on the left. Let's see how the magnetic susceptibility matches. Okay, so the orange arrows are middle Holocene arrows and potentially middle Holocene soils. Generally the deposits are lighter, and the magnetic susceptibility is not as high. But once you get into the late Holocene, a time when we would expect more forested conditions and maybe more landform stability, you're starting to get these magnetic susceptibility spikes. But we also have things such as between AB2 and AB1, these sedimentation events. So what explains those? Our organic matter is higher in the late Holocene soils. Okay. And then our calcium carbonate content. Now remember, a lot of the additions to these, a lot of the parent material for these soils can be limestone, the regolith. But it also, in this region, you have loess, so windblown silts. And you can see in the lower deposits during the middle Holocene, the calcium carbonate signature is not that high. It's about 7%, and it keeps getting higher. But in the late Holocene, it really picks up. And at first, I thought it had something to do with the limestone additions to these deposits. But that wasn't the case when I did the soil micromorphology. We actually saw a very different picture of what was actually adding calcium carbonate. So soil micromorphology, I basically cut blocks out of a wall. And so you can see here I am cutting blocks out of the wall, trying to get as much of the profile as I can. And these will be intact. And then I put burlap strips that are dipped in plaster around those blocks, and I kind of wrap them like a dinosaur bone. And so I'm able to take them back to the lab and then get them cut into really thin sections. And you can look at them under a microscope and see some interesting things. Okay. So you can see I have a little bracket there. That's the area where I was getting all that calcium carbonate really picking up. And it goes up steadily until you get to this higher part here where it's just chock full of calcium carbonate. There's lots of it. And what I found in the micromorph slides was actually plant ash, a lot of it. And to the point that as these deposits got wet, the calcium carbonate would get weathered, and so the water would pick it up and precipitate it, and then it would redeposit itself within the sediment matrix and what they call a calcitic crystallitic birefringence fabric. But it was just completely calcium carbonate. And so the addition is actually coming from wood ash or plant ash. Okay.
Hey,
So
Justin,
I've covered
you've got about a minute left.
I got 1 minute.
Sorry, we've been having timer problems, but I just wanted to know.
How much do I have?
You got about a minute left.
Oh, I think I can do it. Okay.
Okay.
Thank you. So we've covered a lot of ground, but I'm going to kind of lay it out what I think happened at Crumps Sink, okay? Okay. So between 7,200 and 5,600 years ago, we have pretty consistent sedimentation and weak soil development. We have a couple soils, but they're pretty weak. We're already seeing that hunter-gatherer activities are leaving a signature. This is during the Middle Archaic period and the Middle Holocene. Probably erosion, stuff accumulating. Between 5,600 and 3,900 years ago, we see some more pronounced soil development, but there's still pulses of sedimentation. The plant ash starts appearing in these deposits at this time. And it could be from camp activities. It's likely it's hearths and people doing activities. So I won't discount that. I think that's a part of it. But here's where it really picks up. So we have enhanced sedimentation once again during the late Holocene, when we would expect some stability. And this is where the layer where we have a lot of plant ash. And this actually corresponds in time when we have grassland expansion. We're seeing fire, increased fire throughout the region. We're seeing domestication of plants. So this might have something to do with anthropogenic environments and hunter-gatherers through horticulturalists starting to actually manage an environment. About 3,000 years ago, we have pretty significant soil development. I'm almost there. We have significant soil development, and I think the soil sits here for about 2,000 years, at least. At this time, really interestingly, people start using the cave much more, and they're stopping their activities around the sinkhole. And archaeologically, that's what's happening. You can actually see something going on in the soil record. Maybe it's a stable landform, so it is a stable landform. So after this layer, this lighter layer, actually had a lot of historic materials in it. And this could be an indicator of plow-based agriculture at Crumps Sink, where we're starting to see accumulation of sediment. There's very weak soil development on it. So we can see the traces of these activities and environmental events in the soil record in these sinks and caves. So they contain pretty interesting records. They might help us to better contextualize karst environments today, understand what happened at them in the past, and it could inform present and future management of these environments. I see potential applications to agriculture, restoration, ecology, and questions of climate change in karst regions. There's a lot of people who are involved with this project, a lot of institutions. Two people I'd like to thank in particular are George Crothers and Christopher Groves. Without those two, I couldn't have done this, and it's been a really cool project. So thanks for listening.
Great. Thanks, Justin. We're gonna keep it moving along. You have a couple of questions in the chat box, Justin, when you're done. So if you wanna, you're welcome to answer those.
Great, thank you.
And our next speaker,
our next speaker,
I'll let you introduce.
Yes, our next speaker is Will White, and he'll be presenting a blueprint for the assessment of inorganic carbon flow paths in the Great Onyx Groundwater Basin, Mammoth Cave National Park. And Will White is the Emeritus Professor of Geosciences at the Pennsylvania State University. He is the author of numerous papers and several textbooks in karst hydrogeology and geochemistry. You can go ahead, Will.
And Will, I have your PowerPoint slides.
Bring it up.
Yeah, I'll bring them up, and you just tell me, like, just say change next slide or whatever, and I'll do that for you.
Next slide. Welcome to everybody. See if this system works. The idea is to generate a critical zone observatory in karst. So next slide. Using this concept to try to understand, for the moment at any rate, just the carbon budget in karst. And we don't have such a critical zone at the moment. So in order to construct one in the karst area somewhere, hopefully, you need to be able to delineate a groundwater basin. You've got to sort out the flow paths, and then you actually have to measure the various types of carbon that are moving through the system and how those types of carbon interact with each other. One of the major problems in putting such a feature in karst is that you have this gigantic carbon reservoir in the limestone. Limestone is calcium carbonate. And there's also a very complex interchange between inorganic carbon and organic carbon. Next, please. So here's a sketch of a critical zone observatory. I stole this from my colleague Susan Brantley, who runs the Shale Hills Critical Zone Observatory, which is actually about 5 miles from where I'm sitting in a straight line. And the whole idea is to do what amounts to a total body scan of the planet Earth, in which you look carefully at the soils, the regolith, the groundwater system, the underlying bedrock, and the ways in which elements are interchanged between those particular components. Next. But the problem is, if you want to do a critical zone in karst, let's say Mammoth Cave, right? That's a nice karst. Herein lies the problem. If you look at the entire Mammoth Cave area, you've got a huge, complicated, interconnected system. You have difficulty in establishing basin boundaries. The basin boundaries fluctuate with discharge. Travel times vary from that of a running surface stream to groundwater movement over periods of tens of years. So the question is, can we carve out a small subbasin and treat it as an isolated unit? Next. So the work that's being done at Western Kentucky University, Chris Rose's project, is to try to develop such a drainage basin for Great Onyx Cave. Great Onyx Cave is way up on an isolated corner of Flint Ridge underneath the Mammoth Cave Plateau. It's an abandoned show cave. It has dry upper levels, it has active stream levels, and the water that collects in it apparently drains to the Great Onyx Spring. And they have, from their dye tracing results, have established that brown line, which is the current basin boundary. Outside the boundary, the water that moves into the karst goes to one of the other big springs on Green River. Next. The advantage, if you want to call it that, of trying to work with a karst system, though, is you get all sorts of sampling sites that you don't have available. In the shale hills, for example, they've had to drill test wells and soil lysimeter wells, and the whole thing looks like a pincushion from all the holes they've punched in it. But here you can, there's a cross section, sandstones that make up the ridge top, perched aquifer and the Haney limestone, a lot of cave passage, and relatively dry in the intermediate zone, but there's seepage out at the edge of the plateau where the water is coming through limestone soils. There's some seepage along fractures within the cave system, so you have drip sites that can be sampled. At the edge of the plateau, there are developed these gigantic vertical shafts, and these are sampling points also. And finally, if you're willing to really work at it pretty hard, you can get down to the base level active streams that are drained toward the spring. And of course, you can sample the spring itself. Okay, next. So there's the Great Onyx Spring. That's where the water from this little subbasin comes up. In that particular photograph, it's back flooded from the Green River. So the water is muddy and you're not seeing the outflow. Next. Well, our objective in this talk is to talk about the carbon budget. And you tend to think of the carbon budget as consisting of carbon dioxide, which turns out not to be true. But most of the action, very complicated action, takes place in the soil. Another cartoon that I borrowed from my colleague, but you see soil CO2, which is exchanging back and forth with the atmosphere. They're getting CO2 released from decomposition of organic material from plant roots. Some of it is being converted into inorganic carbon. The inorganic carbon is reacting with minerals in the bedrock. All of that's making its way down into the groundwater. And that's for a conventional aquifer without throwing the special features of karst into the picture. Next. So here's the sources and interactions that you have to deal with. These are kind of broad brush sort of things. There's the atmosphere, where we have a CO2 concentration that's now 0.0415 of a volume percent. I keep having to adjust that number upwards all the time. The bedrock, which has got carbon and the calcium carbonate, and there's the vegetation, which I'm representing as cellulose, the CH2O, but it's obviously much more complicated. The vegetation provides you with some dissolved organic carbon of various sorts, and it provides you with a lot of different sorts of particulates, wood fragments, leaf litter, humic material, and some actual elemental carbon. This interacts with the gas from the atmosphere and from the soil, and ultimately in aqueous solution to dissolve inorganic carbon of aqueous CO2 and then the various carbonate species. Next. So you can try to draw this in the form of a carbon budget or a flow sheet. We have the atmosphere, the sandstone uplands with vegetation on sandy soils, a sandstone underneath that, the Haney limestone, which drains out into the Haney Springs, and the Big Clifty, which is the lowest most of the clastic units, and the Big Clifty drains overland into the soil, which drains into vertical shafts, or down through Vado zone fractures, through maybe the dry cave passages, shaft drains going into active cave streams, and sooner or later it comes out the spring. Precipitation directly on the valley walls through the epikarst and drain also into the shafts. The shafts are important. They act as a short circuit for the runoff from the plateau. Instead of behaving like an aquifer, it's just putting a big heavy copper wire across your electrical model. Next. The inorganic carbon is actually pretty easy to deal with. The carbon, if you simply look at it as elemental carbon, is simply the sum of the various carbon-bearing species. So aqueous CO2, carbonic acid, bicarbonate, carbonate ion, aqueous CO2 and carbonic acid you take together because you can't really tell them apart very well. CO3, the actual carbonate ion, is actually negligible at the pH of most karst groundwaters. So you can put the chemistry together and you find that you can actually calculate the carbon in terms of the bicarbonate, which is a measurable parameter, and the pH, which is a measurable parameter. And so dissolved inorganic carbon just multiplied by the atomic weight of carbon, and you can get the carbon load in kilograms per cubic meter. Next. So what do we actually know at the present moment? Now, I don't know how much Chris and his gang have in their back pockets that I don't know about. But beyond that, there was measurements made of soil gas by Franz Dieter Miotke back in the mid-70s. And on Flint Ridge, which are thin, sandy soils, the carbon dioxide in the soil atmosphere is around 0.5%. And the same is true in the soils in the bottom of Cedar Sink. They're a little higher out on the sinkhole plain. It turns out the big carbon reservoir is on the silt terraces. You measure these on the silt terrace outside downstream from Echo River Spring, and that gets as high as 5% CO2, which says there's a big organic reservoir in the silts. And those backflood into the cave system. So some of the present cave sediments and maybe some of the sediments in the abandoned upper levels have more carbon content than maybe they've been given credit for. Next. We have a lot of data on CO2 in the Haney aquifer from Jack Hess's thesis data way back when. The interesting thing is that the water coming from the Haney Springs is incredibly undersaturated. The water is pouring through without reacting very fast with the limestone. Next. The deep aquifer, the main cave-bearing system, there are data on shafts, drips, and springs in different color coding. And most of the waters in the cave are actually undersaturated, which means that they're absorbing CO2 from the atmosphere, but they're releasing CO or carbon from the limestone. And of course, the supersaturated ones are the ones that are making the speleothems out near the edge of the plateau. Next. So, okay, let me wrap this thing up, or at least I think I heard the warning buzzer go off a moment ago. So the internal drainage lines, the active cave streams discharging to Great Onyx Spring, some of them at least have been established. There are high quality maps of the cave systems, thanks to the work of the Cave Research Foundation. Soil sampling sites and sampling at Great Onyx Springs have been established. We need better precision for the basin boundary so you can do more accurate budget calculations, more sampling sites, sampling protocols, but it overall looks like maybe you can do something with this particular location. Let's see, right next. So that is a quick overview of what might be done in the future. Thank you very much.
Awesome. Thank you, Dr. White. I'm going to stop sharing my screen, and we do have a couple minutes if we have any questions. It looks like we do have some in the chat here. I'm just going to read them for right now. Looks like we have a question from Chris Groves. He wants to know, his comment says, will the cross section you showed, which is very similar to the one in one of your books with caprice shafts, speleothems, etc., moving from the entrance, matches the Great Onyx Cave perfectly. He wants to know if you had that cave in mind when you drew that originally, or was it just a genetic composite?
Actually, I drew that cross section about a month ago or something like that, but it's a very schematic, cartoonish sort of cross section. But I did have Great Onyx Cave in mind because there are shafts that cut through Great Onyx Cave, partway along the main trunk passages.
Awesome. Are there any other questions? Feel free to send it to the chat. Otherwise, we will continue on with our next speaker.
Okay, so our next speaker is Sonia Meyer, and Sonia was the Natural Resource Management Assistant at Carlsbad Caverns National Park, Carlsbad, New Mexico, during summer of 2019. Sonia, she conducted her research on carbon dioxide and how visitation was affecting air quality in the cavern. Go ahead.
Hi. So I did this internship through the Mosaics in Science program sponsored by the National Park Service, Environment for the Americas, and the Greening Youth Foundation. So this was about how anthropogenic carbon dioxide is affecting the air quality in Carlsbad caverns. This is my abstract, but I'll be talking about this throughout the presentation. If you've never visited New Mexico, this is kind of what the landscape looks like above ground. 500,000 Mexican free-tailed bats roost in Carlsbad caverns, and they, during the summer, they exit every night. It's very beautiful. And then a photo of the cavern itself. So if you're not familiar with the area, let me see if I can turn on my annotate. So a typical journey through the cave is to walk down the natural entrance this way. And then you would go down to the big room junction. And this is kind of the central point where everyone in the cave will pass through. If you don't go in the natural entrance, you might go in the elevator, which is here. But no matter which entrance you take, you will either go in the natural entrance, or you will definitely pass through the big room junction. So that's why we place some of our monitoring stations there. And then from this point, you would typically do a loop around the cavern and then come back again by the big room junction and either exit via the elevator or the natural entrance. Okay. So the purpose of this project was part of the visitor use management study, which is a larger framework across the National Park Service. And the main idea is to measure current, so when you're starting the project, you measure current conditions in the cave for whatever variable you're looking at. And in my case, it was anthropogenic carbon dioxide. And then you set up an interval, say 5 years, at which you measure the carbon dioxide levels again every 5 years. And at the outset of the monitoring, you want to set parameters for which the levels are too high. And if those carbon dioxide levels ever exceed those parameters, then you would want to reevaluate and maybe make some programmatic changes to the way that the park is being managed. So this is a really important management tool to make sure that everything is in line with conservation goals. So this was the very start of the visitor use management project for carbon dioxide in Carlsbad Caverns. So the main goal was to begin measuring the carbon dioxide, as well as do research on what limits we want to set, but that was fundamentally a decision for the park management. So my role was mostly measuring that and doing literature research on the impacts of elevated carbon dioxide. So the first one is visitor safety. Let's see. So I did a lot of research on what levels of carbon dioxide are safe for humans. Just to give you an idea, 400 parts per million is the typical outdoor carbon dioxide levels. For indoors, less than 1,000 is considered good. 1,000 to 2,000 is less than ideal. Over 2,000, ventilation is necessary, and you start to see health effects at 5,000 parts per million, which is actually the workplace exposure limit, which is 8 hours a day, 5 days a week. So to give you an idea, during the summer that I was there, the carbon dioxide was reading at about 1,500, so it was in this range. So it was definitely safe, but less than ideal, especially for a national park. You know, you want to have good air quality, as well as a good visitor experience. The other, so visitor experience as well. The other impact is that it can slow speleothem growth. So I've previously given this presentation more to lay people, so I probably don't need to explain it as much here. But basically, when water drips from a stalagmite, the degassing process is what allows the deposition of calcium carbonate, which is what forms speleothem. And if the carbon dioxide in the air is too high, it'll throw off the equilibrium and actually prevent degassing, which then prevents the deposition of calcium carbonate and slows the growth of speleothem. And then finally, I did find one research article, although I couldn't access the full research, but there is a limestone corrosion threshold, and I believe it was 2,700 parts per million. So at 1,500, we're still below that threshold, but I definitely think that any limit that the park would want to set would be below the limestone corrosion threshold. And then I also did some other research about airflow in Carlsbad Caverns conducted by Dr. Fleisch and his graduate students. And the airflow obviously is very important because of how that affects the carbon dioxide that's in the air. So the Carlsbad Cavern is known as a cold trap cave. In the winter, the cold air, which is denser and heavier, flows down the natural entrance and settles at the bottom of the cave here. But in the summer, the air does not sink, and as a result, the air is pretty stagnant. So in the winter, you get a lot of airflow, a lot of movement, and in the summer, you do not. Dr. Fleisch also conducted research on barometric versus convective ventilation and found that the left-hand tunnel was barometric, which is quite interesting, and as expected, the rest of the cavern is convective, which is this whole area here. And that is most of the area that we were looking at. To go to the left-hand tunnel is a paid tour, so most visitors would be staying in this area rather than going to the left-hand tunnel. This symbol is quite interesting, which covers this area of the cave. Basically, during the research project, the cavern shut down due to a government shutdown. And in that 1 month period of no visitors, they were able to see a very strong drop in temperature. So they concluded that air temperature in these areas are strongly affected by visitors. And I would think that carbon dioxide in these areas would also be strongly affected by visitors as well. So to measure this, there were some previous monitoring efforts. Previously, they used a device called a telaire, and when I arrived, I was given a device called a Wöhler, and the sampling rate was 5 minutes. The telaire had been running for a couple of months, but when I arrived, I checked the calibration for the device, and I found that it was not calibrated, and I wasn't confident in the data that it had produced. So I kind of started over with the Wöhler. This is the Wöhler device. Important limitation to note about the Wöhler is that it caps at a range of 2,000 parts per million. So we were measuring at 1,500 parts per million when we started. So there was kind of a risk that it could possibly exceed 2,000. It never did, but when we started, that was something that we were aware of as a limitation. So there were 3 devices, and we placed them in the elevator, the Big Room Junction, and King's Palace. I'll talk about each of these locations. This is the elevator location. The reason we placed one here is this was actually our greatest concern for the buildup of anthropogenic carbon dioxide. As you can see, and this was taken in 1971, and Visitation has increased since then, but you can see that there are very long lines. So especially in the holidays and weekends in the summer, you see very, very long lines of people waiting for the elevator to get out of the cave. And with people just standing there for such an extended period of time exhaling, we were concerned that there might be a health risk for carbon dioxide in this area. The next spot was, as I mentioned, the Big Room Junction. We chose this location because of how central it was to all the visitors in the cave. We also had a sound monitor here as well. So I had wanted to correlate the sound monitor data with the carbon dioxide data. And then the last spot is the King's Palace, which is over here. And this is a photo of the King's Palace. This one was chosen because you need to pay for a separate tour in order to visit this part of the cave. And I thought it would provide a really interesting time correlation with, because we have timed entry, we know exactly how many people are going into this area. So I thought we could really see the effect of anthropogenic carbon dioxide on the environment. So calibrating the devices actually was a big problem. These devices are German, and they were recommended by Dr. Fleisch, and the instruction manual was translated from German, and I guess I misinterpreted the part on automatic baseline calibration, and I did not realize this until the end of my internship because I didn't have computers. I'm assuming some of you work for the government. It took me nearly my whole internship to get computer access. So I couldn't look at any of my data until the very end of my internship. And I found that there was a big problem with the data. So basically, the Wöhlers automatically calibrate to atmospheric carbon dioxide levels, which are about 400 parts per million. As you can see, these are all reading about 400 outdoors. And what it does is every about 7.5 days, it will automatically recalibrate, assuming that it has had a dose of fresh air, so to speak. So imagine that the device is sitting in the cave at 1,500 parts per million. And that's the lowest reading that it's gotten. It will recalibrate and say that 1,500 parts per million is now the baseline of 400 parts per million. So what this ended up in, you can see the red data is the original data. So this is also original. This is before the first automatic baseline calibration, and then you see a big drop. So that's the automatic baseline calibration, then increase. There are some gaps in data, and we had, these devices were not battery powered, they were plugged into an outlet. So there were some issues with power outages. And what happened? There was an issue where it doesn't save the data if you unplug it without saying stop. So I lost data for those reasons. And then you can see here that it continues, another drop right here for the baseline, it continues, and then another drop. So like I mentioned, I couldn't see any of this until the end of my internship, which was unfortunate. So what I did was I just mathematically corrected everything. So with a drop, I just moved all the data up. With these gaps, I did linear regression to kind of do my best estimate of what it should be at that point in time. And then I also recalibrated the device at the very end, so I kind of knew what the end was supposed to be. So as a result, this data is definitely not that valid, I would say, but I think it's still a good starting point for the rest of the monitoring project. But as you can see, there still are definitely like very clear trends, one of which is that the carbon dioxide is rising over time and not returning to the baseline level from week to week. You can see the peaks here. These are weekends. This one is probably a holiday or something. And then you can also see the opening hours. Each of these peaks is 8 to 6 p.m., which is when it is opened. And then you can see after the cavern closes, the carbon dioxide level kind of slowly relaxes until it hits 8 a.m. again, where it shoots up. So you can see that pattern repeating over and over. So it's very clear that there's anthropogenic influence on the carbon dioxide. Again, related to data quality issues, you see I only have the elevator and the big room junction here. King's Palace was very severely affected by one of the thunderstorms that caused a power outage in the cave. So I lost nearly all the data for that location. But here we have correlations between visitation. And so visitation was determined simply by the number of tickets sold, and I got this information from the fees office, compared to the daily normalized carbon dioxide values. So since the carbon dioxide was rising every single day and never returning to a baseline level, we had to normalize the data so that we could compare it to visitation from day to day. And what we did was just look at the I think subtracted the value from the start of the day from the previous day so that we could normalize it. What was the starting carbon dioxide value versus the ending carbon dioxide value. And then some other things that we found.
Sonia, you've got about a minute left. Our tone's not working.
Oh, okay. All right. So I just wanted to show that how far below the OSHA safety limit we were. So this is the OSHA limit up here, and this is our readings over the summer. So there's definitely, in terms of safety, we're doing pretty good, but in terms of conservation, you know, the 2,700 limestone corrosion threshold limit is over here, as well as wanting to have a good visitor experience. I definitely think we want to be lower than the OSHA safety limit. So in conclusion, there were limitations, the first of which was the short range of my internship, and they have continued the carbon dioxide monitoring, I think for a full year since I've been gone. So they should have good data now. The data losses due to the automatic baseline calibrations were problematic, as well as the power outages and other issues. So yeah, they've continued the monitoring, so I haven't heard you know, what it's been like since then. But what's really exciting is that you could do a predictive model to determine the carrying capacity of the cave based on the carbon dioxide limits that you want. And there was some research on this in a cave in Spain. So I think that's a good path forward for the next steps. So yeah, mostly the strongest conclusion was that there is definitely a correlation between carbon dioxide and visitation, which is kind of what we expected. Due to the patterns in the cave, we expected higher carbon dioxide in the summer and lower in the winter. And I believe that the levels did drop pretty significantly this past winter, although I haven't looked at the data very thoroughly. Lots of references. I want to thank Erin Lynch, who was my supervisor, as well as everyone at Carlsbad Caverns who supported me doing this research, as well as the sponsorship agencies for the internship. And thank you all for listening. Yeah, does anyone have any questions?
Awesome. Thank you so much, Sonia. That was really cool work. And I totally understand what you mean when you're like, oh, I'm working for the government. I'm an intern at Mammoth Cave, so I totally feel you there. There may be, if you have any questions, feel free to put them in the chat for Sonia. Chris Groves does have a question. Chris, I'd ask that you send your question in the chat to Sonia, because we have one more presenter and we are about 15 minutes behind, so I apologize everyone, but thank you so much for sticking around to the end. Adam, if you would like to introduce our last speaker today.
Yes, our final presenter is going to be Rosangela Addesso, and uh-oh, my computer just went blank, so I'm trying to pull up your bio. Sorry.
Rosangela Addesso.
Yeah, my bad.
It's difficult to pronounce.
Yeah, I knew I was going to butcher it, and I'm sorry.
Don't worry.
A PhD student with the Department of Chemistry and Biology at the University of Salerno. She's an ecologist and speleologist for passion. The topic of her PhD project is monitoring of waters, atmosphere, and sediments of the Pertosa Oletta cave, a show cave in the Campania region of South Italy, looking at the impact of human visitation to the cave ecosystem while developing a model for sustainable management of cave tourism. So I'll let you take it over, and thank you.
Okay, thank you for this presentation. Hello to everyone. I am the last one finally. I think that we are all tired, but I will try to be as clear as possible. Okay, I want to start with a short introduction about the impact of tourism in Show Cave, because beyond visible impact that we can see with our eyes by contact with the mechanical destruction of speleothems, we have all other sneaky forms of impact that we can't see with our eyes, such as the increase of carbon dioxide or heat as a result of tourism breathing, but also introduction of spores, seeds, and organic matter by humans. But one of the most important problems that actually grip the manager of Show Cave is the development of Lampenflora or rock surface due to the artificial light. But what is the Lampenflora? It means the flora of the lamps, and it is indeed an alien of the caves. In fact, we know that in cave there isn't the light, but we bring inside the light for tourism, and all these spores, these seeds of plants, can proliferate because they can find inside the cave high humidity, but also the light, and can proliferate, covering all the surfaces. Lampenflora is mainly composed by cyanobacteria, algae, but also mosses, lichens, ferns, and fungi. And it can provoke a lot of problems. First of all, biodeterioration of surfaces, because they can produce organic acid from their metabolic activities that can alter and dissolve the substratum. In fact, as we can see in the photo, when you go to sample the Lampenflora, the layer on which the Lampenflora rests is completely corroded by this acid substance. But there are also structural problems. In fact, some species composing the Lampenflora community can go inside the crack crack of surfaces, rock surfaces, and can provoke the loss of cohesion or disintegration of the substratum. But there is also an aesthetical problem because they cover all green surfaces, and among them, we have also impact and effect on vermiculation that we can see below. Vermiculation are deposits of incurrent particles, mainly composed by calcite, with a minor content also of quartz and clay minerals that we can find on walls and ceiling of a natural and artificial cave. And we don't know the origin of this deposit, but we have already damaging them. So the aim of this study is to shed light on the efficacy of chemical and physical growth control treatment, as well as the alteration and effect that this kind of treatment can activate on surfaces covered by Lampenflora, with the definition of mitigation strategies of the damages. This study is conducted in Pertosoletta Cave in Campania region in the south of Italy, in the lead trail that we can see in green in the photo. But I want to specify that this is only a part of a big project, of my big PhD project, that is based on a continuous and complete environmental monitoring of all compartments of the cave, so water, atmosphere, and sediment. But here I'm presenting only the preliminary result about the treatment of Lampenflora and on surfaces. What are we doing? We are monthly carrying out chemical and physical growth control treatment for 1 year in the lead trail on bare surfaces without vermiculation and with vermiculation. On surfaces with size of 50 times 50 centimeters, using commercial bleach and hydrogen peroxide for chemical treatment, and an UVC lamp for the physical treatment. And I'm monthly monitoring chlorophyll fluorescence using a minipam that give us information about the photosynthetic activity of this Lampenflora community. And at the end of the year, we will carry out a lot of other analysis, geochemical and microbiological analysis associated with microscopical analysis that give us other information about the alteration activated on surfaces. Here we can see some of the delimited area that are object of treatment. Below we can see one of the UVC lamp that was provided by Suggest Company, that is a local company. And on the right we can see me attached to the wall during the treatment. So we can see some photos about the chemical treatment with the commercial bleach before and after the first treatment, and surfaces covered by Lampenflora with and without vermiculation. As we can see, already after the first treatment, we have the surfaces completely cleaned. This because we know the efficacy of commercial bleach, because it's one of the most methods used in cave to solve this problem with the Lampenflora. But we know also the toxicity of this substance, and it's important to understand what happens on surface over time after numerous treatment. And it is for this that we choose also this kind of method to follow over time what happens. Here we can see always the surface is treated with the commercial bleach. As we can see, after the treatment, a lot of dead organic matter rests on surfaces, and as we can see, fungi intervene to their decomposition. In white we can see mold. Here are shown photos about the treatment on surfaces without vermiculation, always chemical treatment, but with hydrogen peroxide. As we can see, over time we have a light brightening of surfaces. But after the third treatment, exactly after 3 months of lockdown for COVID without treatment, we can see a slight recovery of Lampenflora. There is a greener part of surfaces. I don't know if it's clear with photo, but then we can see also the data that confirm these things. Therefore, we don't have apparent and evident effect on surfaces. Here, instead, we can see treatment with here we can see photos about the treatment, always hydrogen peroxide, but on surface with vermiculation. And as we can see also in the video, this kind of method is very, very aggressive for vermiculation matrix. It corroded completely the matrix, destroyed them. For this, maybe is not recommended this method for surfaces covered by vermiculation and Lampenflora, obviously. Here are presented the data about maximal photochemical efficiency of photosystem 2 that give us information about the photosynthetic activity of Lampenflora. We have the 3 treatment, more a control, plus a control. And as we can see at 0 point, we can have values around 0.700. And after the first treatment, we have similar values for commercial bleach and hydrogen peroxide treatment that are around zero. And it did not change after 1 month and nor after the second treatment. What happens? But what happens after 3 month break without treatment? We have a slight recovery of Lampenflora, as we can see here, on surfaces treated with hydrogen peroxide, stopped immediately after the third treatment. The UVC treatment instead didn't show effect. Maybe we have to increase the number of treatment on surfaces, maybe every night or every week. And we are working for improve this part of the treatment. Here we have the data about the same treatment, but on surfaces without bleaching. As we can see, we have the same trend and same efficacy of this treatment. And this is confirmed also by the 3-way ANOVA. There are significant differences among the time treatment and among the typology of treatment, but any difference occurs among the surfaces. In conclusion, what can we say? That hydrogen peroxide and the commercial bleach treatment showed both efficacy with an almost complete reduction of biological activity. The surfaces interested by hydrogen peroxide treatment showed sign of recovery after 3 months without treatment, unlike the conventional bleach. And this kind of treatment damaged visible vermiculation. For this, it is not recommended for this kind of surfaces with vermiculation. Finally, regarding the UVC treatment, it didn't show effect in relation to the photosynthetic activity, and we increased the number of treatment every week before, but maybe after, if we don't have effect, probably we will do every night this treatment. And now we are waiting the end of the year when we will carry out all these analysis that give us information to evaluate potential effect of the treatment on surfaces, both chemical-physical but also biological point of view. And now I want to thank my university, it is the University of Salerno, but also the University of Bologna, with which I'm cooperating for this, but also the Mita Foundation, that is the manager of Pertosauletta Cave, and also these 4 speleo groups that help us with with operation, the technical operation. And finally, I want to thank you for the attention. And I left my address, email address, if you want to do some question or give me feedback about this project. Many thanks.
Awesome. Thank you so much, Rosangela. It was really great. I know we have a number of questions from Rick Toomey from the National Park. I think, Rick, you should be able to unmute yourself right now if you'd like to ask your questions.
Well, this is Rick. Can you hear me now?
Yes, we can hear you.
Okay. My biggest question is, how much time did you expose the Lampenflora with the UVC for the treatment?
8 hours. 8 hours in the night.
Wow.
So for safety of tourism, we use this kind of treatment in the night. But I think that we have to increase the treatment maybe each night, every night, because I think it's not efficacy.
What wattage were your UVC bulbs? Or how much UVC were you?
Sorry, can you repeat?
Either did you have a luminosity, UVC luminosity, or do you have a wattage for the bulbs? I'm trying to get an idea of how much UVC how much energy was hitting the algae.
Okay. Unfortunately, I don't have this technical information because the project is started recently, and I have I haven't still the technical composition of light, but
okay.
we asked this company to provide for us this kind of lamp. But if you write me in private, I can ask, and then I can give also this information to you.
Because we are also doing some experiments with UVC, with shorter duration, but I'm interested in talking about that. Also, during the lockdown, were the lights, was the cave still running? I'm wondering why there was growth during the lockdown.
Can you repeat the last thing? Sorry. Or can you write? I don't know. Because
okay. During the lockdown.
Yes.
Why was there algal growth? Why did the peroxide start growing algae? Were the lights still being turned on and off?
Yes, because there is a break to the control unit also in this point, and we have the light also during the lockdown. we are lucky for these things.
Okay.
It is a turn on during the 3-month lockdown.
Okay.
In that point where we are doing the treatment, the control unit lamp is a break.
Okay. We've had that problem here as well.
Okay. And the light is always open, is always turned on.
Okay. Thank you.
Awesome. Thanks, Rick, for your questions. Thanks, Rosangela. Or does Val, I think Val has a quick question.
Well, and hi, Rosangela. Good to see you again. Enjoyed your talk.
How are you? I saw the photos.
Oh, good. Yes, you were in them. And I'm wondering, what was your contact time on the H2O2, on the hydrogen peroxide?
I know that you should come here, not? Or not?
Oh, yes. We have plans to come to Pertosa. So I'm wondering about contact time on the hydrogen peroxide. How long did you leave the hydrogen peroxide intact with the cave surfaces?
How long the hydrogen peroxide?
Contact time for H2O2.
I don't understand.
I'll type the message.
Yes, you can write. It's better.
Great. Do you have any other questions then? Well, Val's typing that into the chat.
On cave surfaces. I did the treatment with the spray, maybe 5 ml milliliters of no 50 milliliters of hydrogen peroxide on surfaces. But I don't know because it reacts. And I think that for 10-15 minutes it continues to react and then finish the reaction. It's clear, Val?
Yes, thank you.
Okay.
Awesome. Well, thank you everyone for sticking around to the end. We had some awesome presentations today. It was really great to get to listen to everybody. That brings us to conclusion of this conservation tools session and the conclusion to the first day of the Karst 2020 conference. So I'm going to turn it over